We are trucking right along here on this week's material. I'm still talking too much. Can't help it. So to introduce this idea of vector spaces, there's a separate video, hopefully you've watched it, left you space for notes for it, but they talk about vector spaces, and basically they give you this lovely definition. They give you this lovely definition here, and they give you our 10 axioms. So these are called axioms. Axioms are like theorems light, kind of. Just go with it. So as long as all 10 of these things hold true, that is basically what this is saying is that it's closed, so that our set needs to be closed under addition and scalar multiplication. Now you'll notice that a lot of these properties here, a lot of these axioms look a lot like the properties that we already have for vectors, which means that a lot of the things we've already been talking about are already subspaces. So we'll keep coming back to this, to these 10 axioms and talking about them. Just a couple of other little random ideas about vector spaces. So far the spaces we've already talked about, so our real number system is a vector space. It's a vector space where every element has one thing in it, right? Our R2 is a vector space. Our R3 is a vector space. In fact, any R sub n, or R to the n, is a vector space. So these are all vector spaces. The vector space made up of the zero matrix, or the zero vector, is also a vector space. This is called the trivial vector space. And then I wanted to just readdress that idea of polynomials always being a vector space. So hopefully that kind of makes sense. So all of our rules hold true for polynomials. So they also represent a vector space. We're not going to really do much with those, but so let's talk about some vector spaces. Let's decide if something is a vector space. So this vector space is A and 2A. So you'll notice that we at least have some relationship between these two things, right? In the vector space video that the Trev tutor showed you, they showed you a couple where you had like xy as a vector. What am I clicking on? Who even knows? So we had xy as a vector, and it turned out that that was not a vector space because, especially when you limit the domain of that, that it wasn't a vector space because either x plus y or x times y caused violations when you did stuff, but these were not related in any way. Now, in ours, A and 2A, they're related. There's that little means is an element of, and again, this means the real numbers. So it's an element of the real numbers. This notation means this is a set. So this is the set of all vectors that meet this criteria. And then this little line, these little double things here mean such that. There's a whole sentence in here. This means, so we're gonna decompose this sentence really quick. So this statement says, written like this, says that the vector space, so this says that V is the set of all vectors A to A, such that A is a real number. That's what that means. So it's all the possible vectors that could ever happen there. And it turns out if we think about how this works, so if x is a and y is 2a, well, oh, hey, isn't that the line y equals 2x? Doesn't that kind of make sense? So this is a line. This is a line, and it goes to the origin. So if we run through our just quick little just real quick through some of these things. If you think about a and 2a being, so there's our vector, so we'll let that be u, and we'll let v be, I don't know, b and 2b. Does it make sense that if I add those two things together, so if I have a plus b and 2a plus b, I've skipped a couple of moments here, but I have this and this are the same, right? So even though I don't know what a and b are, those are the same. So my relationship that the top one and the bottom one have a similar factor holds true, right? I could show the same thing for principle number, for principle 2, right? If I reverse that, b plus a is the same as a plus b. So axiom 2 holds, axiom 3 holds. If I threw another vector in there with a c and a 2c, again, I can factor that guy out and show you that. The 0 vector, right? If I let a equal 0, so if I let a equal 0, then my vector is 0, 0, which is the 0 vector. And so my 0 vector is in that space. If I take a, 2a, and I add to it negative a and negative 2a, oh, hey, look, I get the 0 vector out, right? Which is principle 5 or axiom 5. 6, so hopefully you kind of get the idea that yes, this is a vector space. Absolutely. So that is a vector space. So let's talk about subspaces. So a vector subspace is a vector space that's inside of a vector space. Kind of like how we talked about, and this will actually come up again, right? When we talked about linear transformations, we talked about going from a domain to a codomain. And then we talked about the range being a set of numbers inside that codomain. That's what a vector subspace is. So a vector subspace is a subset of that vector space that's also a vector space. It's just a smaller one, right? I guess another analogy might be something along the lines of if you think about rectangles and squares, right? The set of everything that makes up a rectangle might contain squares, but all of the squares is a smaller subset than the number of rectangles, right? But I don't know if that helped. So in order to show that something is a vector subspace, the first thing that we have to show is that the 0 vector of our original vector subspace is also in our new vector subspace, or in our vector space. I keep saying subspace. This is our vector space. That's the big guy. This one's our subspace. That's the smaller guy. So as long as the 0 vector is in our subspace, we're good. It needs to be closed under vector addition. So again, that just means that if I add two things that are in H, that also needs to be in H. And it needs to be closed under scalar multiplication, which means that if I multiply something in my subspace times a constant, that the new vector is also in my subspace. Hopefully that makes sense. So it's kind of like we're taking the vector, so yeah. So is our trivial vector space a subspace of R2? So let's talk about that. Well, the first principle is that the 0 vector needs to be in H. Well, it is the 0 vector, so A is good. Okay. The second one is that it's closed under addition, right? And I don't know about you, but 0, 0 plus 0, 0 all day is equal to 0, 0. This is an element in H, just like each of these is elements in H. Okay, so the sum, so we are closed under addition. Last one says that if I take a scalar and I multiply it by that, so I don't know, 372 times the 0 vector here, is equal to the 0 vector. And again, this is an element in our subspace H. So yes, H is a subspace of R2.
For my next trick, let's go back to that vector space we defined earlier with A and 2A. We already said that this is a line, and we've already proved that it was closed under addition and closed under scalar multiplication. So all we need to show here is that the 0 vector is in it. Well, if A is 0, then we get 0, 0, and that is an element of, so that's in H, which means that yes, this is a sub vector of R2. Last example on this page is asking about whether or not the real numbers is a subspace of R2. So R2 is our Cartesian coordinate. Now, if we think about what the elements of each of these things look like, things in R are going to look like, I don't know, like 2 or 7. And things in R2 are going to look like 2, 7. One of these things is not the same. So the elements of each space, vector space, are not the same. They're not the same type, right? So in here, we're talking about vectors with 2 elements. Here, we're just talking about single numbers. So because they're not the same type, there's no way that I could transform or that I could talk that this is a subset of, so no, R is not a subvector, the subspace. Subspace. Let's try that again. Oh, I did that up here too. Subspace. A subspace of R2. So let's take the same idea and think about things that actually are in that subspace. So things that actually are in that space, but whether or not that actually is a subspace. So if we think about a plane that does not, made you dizzy, that does not go through the origin in R3, so talking about, I don't know, some plane up here, looks kind of like this. Why not? Because it doesn't go through the origin, that means that 0, 0, 0 is not in the plane. So because it's not in the plane, that means that this plane is not going to be a subspace of R3, right? So one of our qualifications is that the 0 vector has to be in it for it to be a subspace. Same idea with a line, right? If we're talking about an R2, we're talking about a Cartesian coordinate. If my line goes somewhere up here, well, the 0, 0 vector is not on the line, so they are not subspaces. So this line is not a subspace of R2. So be careful. Just because it happens to exist in that vector space does not necessarily make it a subspace of something. Just throwing that one out there. All right, let's talk about just a real quick couple more things. So this theorem says that as long as my vectors are in the vector space, then the span of those vectors is a subspace of that vector. So this time, so again, we can think a little bit about our Cartesian coordinate again. So let's say our vectors are in the R2 space. That would mean that it doesn't matter what our vectors look like. Okay, so here's maybe vector 1. Here's maybe vector 2. And we know that the span of these things, so if they're not on the same line, we know that in R2 that the span here is equal to the plane that contains them both, right? If they happen to be on the same line, so maybe V2 is this one, then we know, here, we'll make that V3, right? The span of V1 and V3, I'm losing my notation, is the line. And that is, because it goes through 0, 0, is closed under addition, closed under scalar multiplication, excuse me, that they are both subspaces of R2. Another way to say this is using that idea of linear combinations, right? We know that the span of, say, V1, V2, V3, why not, we'll do that, is equal to some linear combination where I have C1 times V1, C2 times V2, C3 times V3, and hopefully this definition can help you see that those all satisfy our 10 axioms of being a vector space. And then the 0, 0 vector, right, if C1, C2, and C3 are all 0, the 0, 0 vector is in there as well. For C1 through CP elements of the real number system. Okay, we are getting close to being done with spaces and subspaces. So we want to show that this is a subspace of R4. So what I need to show is a couple of things. First, if I can show that the span of those vectors is essentially, if I can show that I have the span, that's an element of R4, right? So what I'm going to do is I'm going to try and write this as a linear combination. Okay? So I can take this vector and I can split it up into an A and a B vector. Right? So I'd have A, I'd have negative A, I'd have A, and I'd have 0 plus negative 3B, B, 0, and B. And if I factor the A's and the B's out there, so I get A times the vector 1, negative 1, 1, 0, plus B times the vector negative 3, 1, 0, 1. Well, each of those vectors is an element of R4, right? So this is an element of R4. This is an element of R4. Those are a linear combination, which means this is equal to the span of those two vectors, 1, negative 1, 1, 0, and negative 3, 1, 0, 1. And since these are vectors of R4, therefore this is a subspace of R4, right? Based on that theorem here. Last one, we're going to try and find the value for H here that would make this a subspace of R3. So in order to do that, I need to see, can I make a linear combination of these that equals Y? So in other words, is there some A V1, B V2, C V3 that's going to equal Y? And in order to do that, right, what we do is we set up our augmented matrix. So 1, negative 2, 5, negative 4, negative 7, negative 3, 1, 0, and negative 4, 3, H. So the H is important here. So essentially we want to be able to say, I want some solution, or I want to be able to say that I have a solution to this augmented matrix. So I'm going to do some row operations here and try and get this down to something beautiful. See what we can come up with. So I'm not actually going to have to do all that many row operations. So the first row operation I'm going to do is I'm going to do row 2 plus row 1. And at the same time, why not? Because it doesn't involve row 2, I'm going to do row 3 plus 2 row 1. It gives me a lovely, lovely matrix. 1, 5, negative 3, negative 4, 0, 1, negative 2, negative 1, 0, 3, negative 6, h minus 8. So notice what's happening here. Some things are happening. So now I want to get down to, I'm going to do something to this guy. So I'm going to do row 3 minus 3 row 2, and some fancy things are going to happen. So 1, 5, negative 3, negative 4, that's not changing. 0, 1, negative 2, negative 1's not changing. And this becomes 0, 0, 0, and h minus 5. Now I don't need to go any further with this because I've already gotten down to a state where this is telling me everything I need to know, right? In order for this to be a consistent system, then I need h minus 5 to equal 0, right? Because if h minus 5 equals anything other than 0, it's inconsistent. So anything else, so that tells us that so that in order for y to be in our subspace, to be in our span here, then h needs to equal 5. Hopefully that makes sense. All right, one more section, and then we are done for the week.